Hardware breakpoints. We continue with the bit different kind of breakpoint called hardware breakpoint. Recall that previously we talked about software breakpoints, which are achieved using the int3 instruction. Hardware breakpoints are achieved using a different mechanism inside the processor. They are much more flexible. For example, they can allow us to break when some memory location is being read or written to. This is a feature which is really hard to achieve using software breakpoints with the int3 instruction. As a disadvantage, we only have a few hardware breakpoints. In fact, we can only have 4 at a time, as opposed to software breakpoints where we can have as much as we want. To explain more about hardware breakpoints, let's see an example. We are going to look at serial header.asm. Let's begin by taking a look at the source code. It is pretty short. As the main comment says, this program adds a constant, which is called addConst, to every dword in my list. Let's see what this comment talks about. As expected, we do have a constant called addConst, which equals 7. Then we have a data section, which contains an array of dwords. This array is called myList, and it contains the following dwords: 1, 2, 3, 4, and so on. There is also a constant called listlen, which measures the size of my list, or maybe the amount of elements or dwords inside this list. Next, we have the code of the program inside the text section. The code is mostly just one loop and some initialization. In the beginning, we initialize EDI to be the address of my list, and we initialize ECX to be the amount of dwords inside my list. Then we have the loop. In every iteration, we read a dword from location EDI into EAX. Then we add to EAX the constant addConst. Finally, we store back the new value of EAX into the location in memory pointed by EDI. Then we move on to the next iteration. Basically, what happens here is that we just add the value addConst to every dword inside my list. Which means, for example, that the first dword 1 is going to turn into 8. The next dword 2 is going to turn into 9, and so on. Please make sure that you understand this piece of code before we continue to other things. If it is required, stop the video and take a look at the code yourself for a few minutes. We continue by saving this program, and next we assemble and run it, just to make sure that everything works correctly. As expected, we cannot see really anything. That is because serial header does not take any input from the console, and also it does not give any output to the console. Pretty much, if we don't have a debugger, the operation of this program is really invisible. We cannot see anything from the outside. Let's open a debugger. I copy the path and I paste it into WinDBG. Next, I pick serial header.exe. I got serial header.exe paused, and the debugger is waiting for commands. The first thing that we usually do is put a software breakpoint over the entry point. Next we use the go command to get to the first instruction of our code. Let's open the disassembly view to view more instructions. We indeed got to the beginning of our code. As we can see, those instructions correspond to the first instructions in our program. Let's step a little bit so we can get the address of my list. In the first instruction, move edi my list, the address of my list is copied into edi. We invoke one step, and now if we take a look at the value of edi, we actually have the address of my list. If we wanted, we could use the command dd followed by edi to get the contents of my list. We can see it here. Let's say, for example, that we wanted to pause the program exactly at the moment when this D word is read. We could do this using software breakpoints. We can read the code and understand that the first point in the program where this D word is going to be read is at this instruction, move EAX D word EDI, which reads a D word from my list. Then we could just put a software breakpoint at this location and use the go command as much as we need until we get to this instruction where EDI points to this specific D word. But this is really tedious. Maybe we could find another way, for example using hardware breakpoints. Hardware breakpoints are achieved using the BA command, which stands for break on access. There are three types of access that you could use. The first one is called read, but actually it will detect any attempt to read or write from a certain location in memory. The next access type is called W, which stands for write. This access type is going to detect any attempt to write to some location in memory. The last access type is called E, which stands for execute. This access type is going to detect any attempt to execute from some location in memory. For example, maybe if we try to execute some instruction. In addition to the access type, we have to specify a size. The size could be one of three options if you are using 32-bit mode. The options are 1 byte, 2 bytes, or 4 bytes. And by the way, the E access type supports only the 1 byte size. The read and write access types support all the three possibilities, 1, 2, or 4. We are going to use in this example BA-R4, which means that we want to detect any attempt to read or write from this location. Next, we have to supply the address of this location. In order to get this address, we can just use this number and add the amount 4. Now we press the return key. Let's see what breakpoints do we have at this point. We can see that we have two different breakpoints. The first breakpoint is the entry point breakpoint. The second one is the hardware breakpoint that we have just set. We can see that it has more columns, which are those two, R4. This is how we can identify hardware breakpoints. At this point, we don't really need the first breakpoint, which is the entry point, therefore we can clear it. Let's see the new list. Before we are going to invoke the go command, Let's try to predict what is going to happen. This will help us understand what happens after we use the go command. We expect the target program to pause just when we read from this location. The first instruction which is going to read from this location is this instruction: move EAX dword EDI. We also expect that the target program will pause at the STOSD instruction, which writes to the same location. As we mentioned, the RXS type is going to detect both reading or writing to a specified memory location. Let's use the go command and see what happens. The target program resumed, and then it paused at this instruction, add EAX 7, maybe surprisingly, because we expected that it would stop at this location, move EAX dword EDI. One thing that you should know about hardware breakpoints when using R or W access types is that the target program is going to stop at the next instruction, right after the memory access. And indeed we can see that we stopped right after the wanted instruction. This is not like software breakpoints, where we stop right before the instruction happens. With this hardware breakpoint, we stopped right after the wanted instruction. Let's make sure that we really stopped at the correct time. We can check the value of EDI first. The value that we got is this number, which is exactly the number that we put when we added the breakpoint. Another thing that we can do is take a look at the memory pointed by EDI. We expect to find 6. Let's see what is inside. Indeed, we have 6 inside. We are going to use the go command again. The access type R should detect both reading or writing attempt to the specified memory location. Therefore, we expect that it will stop right after the STOS instruction, which is going to write into EDI. Let's use the G command and find out. Indeed, it stopped right after the STOSD instruction. Let's check the value of EDI just to be sure. The value of EDI has now increased by 4 because of the STOSD instruction, as expected. At this point, we no longer need the breakpoint, so we are going to clear it using the BC command. Now the list of breakpoints is empty. Let's try something else. Let's try, for example, to add a hardware breakpoint with the W access type, which means that we only want to stop at the STOSD instruction. First, let's find out to which memory location we want to detect writes. We begin by taking a look at the value of EDI, and next we can view the memory contents beginning from EDI. What we see in this picture is part of my list. We know that my list begins earlier. Let's say, for example, that we want to find out the exact time where this dword in memory is written to. We could do it using the BA command. We are going to use the W access type with size 4 to detect dword, And next we have to supply an address. We take this number and we add 8 because we want to skip this D word and also this D word. Now at any time where some instruction is going to try to write to this location, we will be able to detect it. Let's take a look at the list of breakpoints. This is the new breakpoint which we have just added. Next we use the G command. I want to mention that we expect the program to stop exactly after the STOSD instruction, which means that we expect it to stop at the loop instruction. We use the G command, and as expected, the target program is stopped exactly at the loop instruction. Let's see what is the contents of EDI. The contents is this value. Let's see what is the D word pointed by EDI currently. It is A, exactly one D word after the D word that we wanted. That is because the STOSD instruction has increased EDI right after it wrote to this location in memory. Let's clear this breakpoint. Now the list is empty. The last access option is E, which stands for execution. We already mentioned that it can only take size 1. Let's see an example of using it. We use the BA command and then we specify access type E with size 1. If we want, for example, to break at this instruction, add EAX7, we could just supply the address of this instruction. As we can see, this location is marked with red. Next we use the go command, and we stop exactly at the expected instruction, add EAX7. This last type of hardware breakpoint, the E-access type, behaves much like a software breakpoint. You might be wondering why having another kind of hardware breakpoint when we can just use a software breakpoint. I want to mention that hardware breakpoint of type E has the advantage of not having to change the target program's memory. I remind you that when we use software breakpoints, we do have to change the target program's memory. We have to change some bytes into the int3 instruction. However, when using hardware breakpoints, we shouldn't do it. Most of the time, those details will just be transparent to you. But there are some cases where it really matters, and you do not want to change the actual memory of the target program. Let's summarize this lesson. We've seen that there are software breakpoints. Those are the breakpoints that use int3, and also hardware breakpoints. This time we learned about hardware breakpoints. Hardware breakpoints are some feature of the processor, and there are only 4 of them. They are a bit more flexible than the software breakpoint counterpart. However, you only have 4 to work with. We can add hardware breakpoints using the BA command. We've also seen that basically hardware breakpoints are meant to detect access to some specified location in memory. And more specifically, it allows to detect 3 types of access. The first one is called R, and it allows us to detect either reading or writing to some memory location. The next one is W, which allows to detect writing to some location in memory. The last access type is E, which allows us to detect execution of some location in memory. This access type really behaves like software breakpoint.